And welcome, Math 3 students, to another exciting EDL lesson. Today we are looking at lesson 7.5 in our statistics unit. You should do the mid-unit quiz as well. So this is kind of our quiz day, but a little mini lesson here to go with it. Okay, in the past we mentioned the normal distribution and we found how to calculate the probability of observing an observation pretty much anywhere on a normal distribution. We just calculated that z-score, or in other words, the number of standard deviations from the mean that we were, and then we could use our handy-dandy table of values. And again, that came from using calculus to find area under a normal curve. But you don't have to calculate it, you just have to look it up. All right, well today, we're going to change it just slightly. We're going to talk about sampling distributions. And the idea here is, a lot of times actually, we're going to take a random sample that's larger than one single individual. So what happens when I start taking samples of groups and then I look at the average of the group? How does that affect our calculations? So that's what we're going to do today. All right, so go ahead and read number 1. You can see average there. There's the standard deviation. But now here's our new piece of information. What if I do a group of 25 students instead of a single student? All right, so first question. If I'm doing a group of 25 and I'm calculating the mean of the group, what do you think the mean will be? Well, if the mean for a single person is 3.4 and I take 25 people and then look at their mean, well, guess what? It's going to also be, on average, 3.4. And there's a formula for this. The formula says the mean of the means is equal to the mean of the distribution. So pretty simple. Mean equals mean. So in this case, the mean of the group will be 3.4. Same as the mean of the distribution. All right, now here's where it's different. What's the standard deviation of the group? Now this should make sense if you think about it. As I take larger and larger groups, I'm going to get less and less variation, right? Think about looking at, for example, heights. If I look at heights of people in a room, there's going to be, if I look at a single person, right, there's going to be quite a bit of variation between the tallest and shortest person. But if instead of just looking at a single person, if I start taking the average height of an entire group of people in, say, my classroom versus the average height of everybody in Mr. P's classroom, you're not going to see much difference there because we're looking at an entire group. So all those really tall people and really short people kind of average each other out. So as we start looking at groups, we're going to have less variation, or in other words, a smaller standard deviation. And here's the mathematical relationship. The standard deviation for the mean of a group is equal to the standard deviation for one subject divided by the square root of the number of subjects in that group. So we mentioned this briefly before, and before, n was 1, so we didn't worry about it. But now we're talking about more than 1. Our sample size here is going to be 25. So for the group, it's going to be 0.35, the standard deviation for a single student, divided by the square root of 25, because that's my sample size. So work that out, and we see that we get a much smaller standard deviation when I'm interested in the average of 25 subjects versus looking at individual subjects, which should make sense. All right, so now we can answer questions about probabilities for groups instead of just single individuals. All right, so what's the probability that the mean GPA for the group is less than 3? Well, guess what? This is normally distributed still, and the mean is still 3.4. Okay, but we now have a new standard deviation because we're talking about a group of 25. Okay, so it's the same calculation we've been doing. We just have to adjust that standard deviation piece. All right, so we want the probability that the mean, so I can rewrite this, by the way, using symbols. So probability that the mean is less than 3. That's another way of saying this whole sentence, but just with symbols. Okay. Well, to find this, we're going to find the probability that we have a z-score that is less than 3 minus 3.4 divided by my standard deviation. So that's how I get my z-score. Working that out, we get a really large standard deviation. Well, actually a very small standard deviation in the negative direction, but magnitude. We have a long, because the standard deviation is so small, we have a very large number of standard deviations in magnitude. Now, when you try to find this on your table, our table only goes to 3.69. Okay, but I need to be 5.71 standard deviations. I'm clear off my table. Okay, and I want to be less than negative 5.71 standard deviations. So I know it's less than 1 minus that number. Okay. So I would say 1 minus 0.999. That is 0.01%. But I know it's less than that because that's for negative 3.69, and I'm way past that. So I could say it's less than 0.01%. It's actually completely acceptable to say it's approximately 0, because if it's less than that, you're pretty much out of area under that curve. So I would accept either of those answers. Okay, now, what if I select one student? Now this is back to reviewing what we did last time. So we're going to say for one student, the mean is still 3.4, but the standard deviation for one student is 0.35. Okay. And now it's what's the probability that my single student, X, right? No bar on that because I'm not talking about the mean of a group. I'm talking about a single individual. So what's the probability X is less than? I'm sorry, not less than. It was more than. X is greater than 3.5. Okay, so again, get your z-score. 3.5 minus 3.4 divided by 0.35. Okay, standard deviation for a single individual. And this gives me a z of 0.29, or a little, just a little above the mean, right? Which makes sense. 3.5, 3.4 are a little above the mean. Okay, look that up on our table. There we are. Okay, but we want to be greater than, and of course this gives me the less than. So I got to do 1 minus 0.6141. Which is 38.59%. All right, on to the next question. We now have a new distribution, so go ahead and read that. Okay, so normal distribution, mean 266, standard deviation 16 days. All right. what percentage of the pregnancies will last between 279 and 280 days? That's a pretty narrow window. I'm going to expect a pretty small percentage, but let's work it out. So, probability, we're between those. Again, I'm giving you a lot more in the way of symbols and notation now. Hopefully this makes sense, and it allows you to convey that all of these words with just this much more concise symbol or symbols. Okay, we got to get our z-score. So 279 minus 266 over 16, that's my lower bound. And then the upper bound, 280 minus 266 over 16. Okay, work those out, and we get 0.8125 for the lower bound z, and the upper bound z, 0.875. Okay, so look those two up. I like to start with the larger. Okay, so, we got to round that off. 0.875, right? Or we only go to 2 digits, so 0.88. Okay, right there. And then look up the lower bound. So again, rounding that one off would be 0.81. Right there. And subtracting, we will get 1.96%. Pretty small chance, and it should make sense because our window is only 1 day. So pretty unlikely that your pregnancy lasts exactly that many days. Okay, next question. This is an inverse question, right? Because here they're giving me the percentage and they're asking me to work backwards and figure out the time. Okay, so longest 25%. Longest 25%. That actually means we want the 75th percentile or third quartile, right? So we need to work backwards. We're going to find the 75th percentile. Okay, so we go on to our table. We find the 75th percentile. So we're looking in here to find 0.75. And it's right in this area. Okay. If we want to make sure we've made it into the 75th percentile, then we got to be up here, right? This one didn't quite make it to the 75th percentile. So if we want to guarantee 75th percentile, then we got to go to this guy right here. Okay, so there's our z-score of 0.68. Okay, so for the 75th percentile, we need a z of 0.68, or in other words, 0.68 standard deviations above the mean. All right, so we can now set up our calculation. Okay, and we don't know how many days, so that's x. We do know everything else. Okay, solve this. We get x has to be at least 276.88 days. Realize it's not perfectly accurate because we didn't hit 75th percentile exactly, right? We had to choose from our table values. If you want to do this perfectly accurately, some of your calculators can. So I'll show you on my calculator. Again, I'm talking about a distribution, so I would go to my distribution menu. This is an inverse calculation, so I would choose inverse normal. And then I tell my calculator I want the 75th percentile. The mean was 266 days, and the standard deviation was 16 days. And there is the more precise answer. But 276.79 versus 276.88 days. close enough, right? That's why our table suffices. We don't need the calculator because we're close enough there. Okay, now the problem changes. We're talking about 60 women. So now the sample size is no longer, we're not talking about one single individual, we're talking about 60. So that doesn't change the mean, but it does change the standard deviation. So the new distribution will have a mean of 266 days. But the standard deviation changes. 16 divided by the square root of 60. That doesn't come out nicely, so I'll just leave it as 16 over the square root of 60 days. It's a little over 2. All right, now what's the probability that the mean of the patients, so we're talking now about the mean of the 60 patients. So we now have a new distribution we're working with. Still normal, still 266 as the mean, but the standard deviation is different. Okay, so we want to find what's the probability that the mean of this group is less than 260. So get our z-score. 260 is my cutoff. 266 the mean of the group. And here's the standard deviation of the group. 16 over square root of 60. Okay, work out a z there. We should get negative 2.90. Okay. We can look up positive 2.90 right there. But we want to be negative 2.90, so we got to do 1 minus that. So pretty small probability, about 0.13%. So pretty darn unlikely. Okay, next page. Go ahead and read the problem. All right, so here we're talking about a mean for an individual car, a standard deviation for the individual car, and then we're going to apply this to 80 cars. Okay, so, and we're going to call it y bar instead of x bar. Bar just means average, right? Doesn't really matter what letter you use for your representing your variable. So this is going to be normal. The mean is still 2.9, but the standard deviation for the 80 vehicles, right, is going to be 0.4 over the square root of 80. Okay, so there's my distribution for y bar. All right, now we're going to do the probability that we end up between 3 and 3.1 with that distribution. Okay, get our z-scores. Minus, sorry. Don't forget that square root of 80, that's where students mess up. Okay, so there we go. Now we just have to calculate these two z-scores and then we can look them up on our table. All right, so the lower bound z-score is 2.24. The upper bound z-score is 4.47, which we already discussed. That's off the table. So being less than 4.47 standard deviations above the mean is pretty much everybody. This is pretty much no area anymore. So the good news is I can kind of just ignore that. So I really only have to look at being greater than 2.24 standard deviations. Okay, so 2.24 is right there. So we want to be greater than that as opposed to less than that. So 1 minus 0.9875. Which is 1.25%, right? Again, I just ignored this. Feel free to try to look it up and go, oh, it's basically 100%, right? It's 0.99999, but it's actually more than that because this is only 3.69. So that's why I just ignored it. I'm basically calling that 1. Okay, next question. This time I notice they're giving me the percentage, so I know this is an inverse normal calculation. Right, I'm going backwards. So I have to use my table, and it is greater than. So 5% on the greater than side, that means 95th percentile. All right, so I look up in my table, I want to find the 95th percentile. And here we are. If we must make the 95th percentile, then we go here. Right? So that is 1.65. So that means my z-score has to be at least 1.65. So plug that in. Okay, we need to be greater than or equal to that. I know that says less than or equal to, but we're basically reading it backwards, right? So the mean of my fleet minus the 2.9 over my standard deviation. Okay, and solve this, and we will find that we need an X bar or a mean of the 80 cars to be at least 2.97 in order to hit the 95th percentile. And there's units here. This is G per miles, gallon. Oh, wait, emissions. I have no idea what the G is. Grams per mile, maybe? Okay, on to the last question. Go ahead and read it. Okay, this one can trick some students. Notice this is the amount that's printed on the bag, but that's not necessarily what's going in the bag, right? The machine is putting that in the bag on average. So my distribution is normal with a mean of 10.2 and a standard deviation of 0.12. Okay, the 10 ounces is just what we printed on the bag because, and this is typical, we don't want to underfill bags. So they normally actually print something on the bag and then set their machines to a value higher than that. That way they hopefully won't get sued for underfilling their bags, right? But some might still be underweight. So let's actually figure that out. What percentage of these bags would end up being underweight, or in other words, below the 10 ounces that are printed on the bag? So probability that X is less than 10. Again, get our z-score. How many standard deviations are we from the mean? So 10 minus 10.2. Oops, I forgot my z there. And work that out. We get negative 1.67 standard deviations. Look on our table, 1.67. But again, this is positive, so we're going to have to do 1 minus that. Which gives us 4.75%. So this company is going to be selling for 0.75% of their bags that are underweight. How could they fix that? What if that's too high? Well, they would just need to turn their machine to a higher amount of chips to put in, right? Or if they could get a more accurate machine, but realize that is likely too costly, or it may not even exist. So if they wanted to lower this percentage, they would need to put more chips in each bag on average. Or they could change the weight that's printed on the bag, but seeing it's 9.9 ounces would be kind of weird. Okay, next question. What if I buy 3 bags? What's the probability none of those 3 is underweight? Well, this is actually not a normal calculation. This is a calculation hopefully you can recall from a previous math class. What's the probability the first bag is not underweight? Well, it's right there. It's 0.9525, right? That's the chances that that first bag is acceptable. Well, what are the chances that the next bag is acceptable given that the first bag was acceptable? Well, it's the same, right? And then what's the chances that the next bag is acceptable? Well, it's the same. So we need all 3 of them, right, to land at 10 ounces or more. So I got to just do that cubed. Okay, work that out. And we should get roughly 86%. Okay, now we're back to a normal calculation here because see, we're talking about the mean weight of, in this case, 3 bags. So we have a new standard deviation on our distribution, right? We want to find the probability that the mean of the group is less than 10. So we get our z-score. And then be careful, we're talking about 3 bags, so our standard deviation changes. We got to divide by square root of 3. Okay, that's the new piece of the puzzle versus up here, right? 3 bags. Work that out, and we should get negative 2.89 for our z-score. So a little less, well, actually, almost 3 standard deviations below the mean, so pretty unlikely. Right, 1 minus that because we're talking about a negative, and we are looking up a positive, so pretty darn unlikely, actually. .19% chance, pretty small. Okay, and last question, what's the probability of the mean weight of 24 bags, right? Where they just changed the sample size on us there, so make sure you pick that up. So we're no longer going to have square root of 3 down here, we're going to have square root of 24. But again, get your z-score. Okay, the standard deviation for 1 bag is still 0.12. That never changes. But we're now talking about a sample of 24 such bags. So I have to divide that by the square root of 24. And we get a z-score that is, again, way off our table. Negative 8.16. So what's the probability that we are more than 8 standard deviations below the mean? That is so rare. Again, our table doesn't go anywhere near that far. So we know it's less than 1 minus this, right? So we know it's less than 1 minus 0.9999, or in other words, less than 0.01%. But it's a lot less than that, right? That's for negative 3.69, and we are way past that. So I'm, again, going to say this is approximately 0. Okay, I would accept either answer, less than that or approximately 0. Realize it is a lot less than this because we are way past 3.69 standard deviations below the mean. Okay, hopefully that was fun and exciting. Good luck on your quiz, and we'll be back for lesson 7.6 later in the week. Thanks.